Hello and welcome to my little video where I will introduce you to my solution to the three indistinguishable dice puzzle. This is a puzzle that was posed a few days ago by Stand Up Math in another video. You'll find it. And the question is, assume you have three indistinguishable dice. He actually had three little dice that are locked up in a little transparent cage, so you really can't mess with them. And suppose you don't want three, you want two dice to roll. How can you get rid of the third die? It would be easy if you could just remove one of the dice, but due to the cage, this is not possible in what he had in the video. You could make some cheating, like say we ignore the one die that is most to the left or something like that, but we are really interested in a theoretical solution to this theoretical problem. So what is the puzzle? Can we emulate, simulate, whatever you want to say, two dice if we only have three indistinguishable dice? Note that because the dice are indistinguishable, it is for instance not possible to pick one of them and discard it, because this cheating that I mentioned, like saying the one most to the left or the one that is furthest away from the other two, this is a matter of distinguishing that is not allowed in this theoretical puzzle. We want to simulate two dice, that is really a pair of numbers from 1 to 6, and we don't want to just simulate the sum of two dice. In many games we are only interested in the sum of two dice we roll. For example, in Monopoly, two dice decide if we walk ahead by 2, 3 and so on until 12 fields, but it doesn't matter if it's this or that combination that shows us the sum. But in other games it's important, for example, to know which two numbers really make up the sum, for example in games like backgammon. And what we'll see, we can even emulate two distinguishable dice from three indistinguishable dice. So what can we already do? We are given three indistinguishable dice, and we can emulate two distinguishable dice. So say we have a result from our given dice like 4 to 5 or 5 to 4 or 4, 5, 2, that's the same because we can't distinguish them. Or another result like 1, 3, 1 or 3, 1, 1 or 1, 1, 3, doesn't matter, these are indistinguishable, and we want to produce a result of two distinguishable dice, and the outcome we've computed may, for example, be, in this case, red 5 and blue 4, which is different from red 5 and green 4, which is different from green 5 and red 4, because these are distinguishable. Or in this case, we might, for example, compute something like red 1 and green 3. Stand Up Math also showed that it is of course possible to make something like that. In doubt, you could just write down a very long table and try to learn it by heart, but we want something that can be done in your head. So, how? Well, the idea is we draw a regular hexagon and label its vertices from 1 to 6. So here's our hexagon, so that we have the vertices in a circular-like arrangement, and we label it with the 6 values that a die can have. What next? After rolling our 3 dice, we connect the values that they show, so they will form a triangle, and then we'll have a look what this triangle looks like. So for example, if you roll 4, 2, 5, we see 4, 2 and 5, and draw this triangle. What types of triangles can result from this? Well, there's the equilateral triangle, that is 3 equal sides, which means nothing else but that we have always change between value exists, value is not seen, value is on a die, value is not seen, value is on a die, value is not seen, in a circular manner. So there are in fact really just 2 cases of this. The one shown and the one rotated a bit. On purpose I left away the labels here because I want to concentrate only on the shapes of the triangle. So, but if we add the labels back for the moment, we see that this would correspond to a row like 1, 3, 5. Remember I started here with the 1. 1, no 2, 3, no 4, 5, no 6. And the next type of triangle is a small, obtuse, isosceles triangle, like this. So we have 2 equal legs, of length 1, and one side is longer. Can happen in different positions. So if we look at this concrete example, that would be from 1 to 6. The next type of triangle is a right triangle, like this. So here we have a right angle. And this specific example would come from 1, 4, 5. This right triangle actually comes in 2 different orientations, so to speak. This is an example of the other orientation. Orientation here means that if we walk around clockwise, in this case we have from the hypotenuse first the long leg and then the short leg, and in the previous case it was the other way around. So like this could come from 1, 2, 4, 5. So we might even have no triangle at all, because we just don't have 3 different values on our dice. So we might have just 2 values. Yeah, that's because one of these is occurring twice. We don't distinguish this in our markup. We just say these 2 values occur. For example, this could be from 1, 1, 5, but it could also be from 1, 5, 5. Or we might even have just one single value, because all 3 dice show the same value. In this case, 2, 2, 2. So this is the complete classification of triangles and not triangles that can occur. Now we have to meet the rules how to obtain the 2 dice from the triangle. First case, if we have only 2 values and we want a simple rule to obtain 2 values, the best idea is just pick these 2 values. So for example, here 1 and 5 occurred, and we just say, well, then we take 1 and 5. Next case, in a right triangle, there's one specific vertex of the triangle that's distinguished, and that's the 90-degree vertex. We pick this value and then the next neighbor in clockwise direction. For example, in this case, the 90-degree vertex is at the 5, and in clockwise direction the next one is 1. So this would be a 1 and a 5. Next case is obtuse isosceles triangle, the small guy here. We just pick the special vertex, the apex of this triangle, and we repeat it. So the small triangles are for double values. Here in this case we see here is our special vertex, it's a 3. We repeat it, so we say it's a double 3. Now we are getting a bit more complicated. We have the equilateral triangle. And this is the first time we have a not so obvious rule. We just pick the smallest of the three values and pick this, and we also pick this value plus 3. So example here we have 1, 3, 5, so the smallest value is 1, so we pick 1, and we have 3, that's 4, so we have 1 and 4. So this gives us only a few cases, because the only other equilateral triangle is 2, 4, 6, and that would give us 2 as smallest value, plus 3 is 5, so that would be 2 and 5. Remains one case on only one value. Here's the rule is simple but strange. We just ignore the value and the result is always 3 and 6. Like even if it's 3 times number 2, we ignore this and say it's 3 and 6. This is motivated because in the equilateral case we just had 1, 4 and 2, 5, and of these diametral cases we were missing just this case 3, 6. So now I showed you how to obtain 2 dice from 3 indistinguishable dice, but I still showed them in gray. How can we make these distinguishable? Well, we can assign colors like I did in the original page. Say one die is red and the other is green, so we can really say this is a red 1 and a green 2, or it's a red 2 and a green 1, which is different cases. And we assign these colors to our emulated dice. And we have to make this choice only, of course, if the values are actually different. If we have two 5s, it doesn't matter which of the 5s is the red one, the outcome is not influenced by this, how we assign. So, how about a little example? Oh, before example, why does it work in the first place? Each triangle that we can draw can be obtained exactly from 6 different outcomes, because we can arrange the 3 vertices and 6 possible permutations. And each pair of 2 values can also be obtained from exactly 6 different outcomes, because one of the 3 dice will show the special value that is only, of course, only once, and the special value can either be the larger or the smaller value. So that's 3 times 2 equals 6. And finally there are exactly 6 outcomes where all 3 numbers show the same value, because there are 6 values. So here's an example. Let's say we roll 1, 1, 5. So we mark 1 and 5. This is the simple case with 2 vertices only, and we said that's 1 and 5 as outcome. And as we just had for our last rule, we say the smaller value is red and the larger value is green. In another case, if we had 1, 4, 5, then we'd have this right triangle, and as we said, we take the 90-degree vertex and go clockwise, so we have 5 and 1, or 1 and 5. What is it? Well, it's green 1 and red 5, because we said if it's not from 2 values, we say red is the larger one. Yeah, that's it. Thank you for watching. I hope this video made the solution easier to understand than the cryptic comment I left at the original puzzle video.